So if we've previously calculated a geometry optimization, we can always use that geometry optimization for additional calculations down the line. And so the easiest way to do that, right, is if we go here and then load it up, right, we have the molecule that we had previously calculated in this case. What we can do now is if we click on this arrow, we can use that input, right, we can use that geometry that we've already optimized to calculate a new property or something. And so, we'll load it up again. It'll look the same. We'll just click on this arrow. It's going to ask us, about the symmetry. Again, right, we're not worried about the symmetry, so we can just, continue without that, especially considering we've already optimized the geometry, so it's already oriented in a way that we would want it to be. So if we click OK, it'll pull up, our options menu again. So now in this case right here, right, the job name, let me just change that real quick. Acetaldehyde. Right, we're going to now, we originally computed it using the B3lib def2tzvp method in this case, but what we're going to want to do now is maybe calculate it using a different method. So if we're going to be using a method that isn't included in this table right here, what we have to do is click on other, and then that's going to give us this option right here, and so now we can type it in. So in this case, I'm going to type in TPSSH and click OK. So now that's going to load in our that method instead. And so if we click on advanced, right, we make sure that everything here is selected that we want to have selected. And so one thing you can do to make sure that that keyword, right, that functional in this specific case right here is going in, is we can click on preview and we can click on generate. And so what that does, right, is it generates what the input file looks like, right? And so this is actually the input file that we're submitting to the cluster and submitting to Orca, and that's running. And so the way that looks, right, if we just do a breakdown of it, is that up here, when you have the hashtags, those are just simply notes that you can type in. The PAL part right here, right, that's how many processors we're going to be using. And then right here, anything that's after an exclamation point is going to be a keyword that we're using. So the important parts right here, right, is that we're going to be using the TPSSH functional. We're going to be using the def2-tzvp basis set, and we're going to be performing a geometry optimization, right, which is signified by the OPT. And then down here, right, what we have is all of our different atoms, and this just simply shows the connectivity, the angles, and the distances that they're having from all the different atoms in these cases. And so, that's why it says referred to as internal in this case, right, because these are all internal coordinates that are all based off of each other. You can also do it via Cartesian coordinates, where in that case, what you're looking at is actual, XYZ positions in space that's going to be listed within the file. And there's some instances where using a Cartesian coordinate system is better than using an internal system. And then for other calculations, right, having an internal system is better than using a Cartesian system. The two numbers that you have after here, right, the 0 and the 1, those indicate first the charge, right? So this is a neutral molecule, so it has a charge of 0. And then you have 1, which simply is the spin multiplicity. And so in this case right here, what spin multiplicity is the number of unpaired electrons times 2 plus 1, right? So because we have 0 unpaired electrons, right, 2 times 0 is 0, plus 1 gives us 1. If we were a system, right, where we had 1 unpaired electron, right, what you have is then 2 times 1/2, right, because each electron has a half spin, so 2 times 1/2 plus 1, so 2 times 1/2 is 1, 1 plus 1 is 2, so for an unpaired electron, system, you would then have what's referred to as a doublet, right, that would be just simply a number of 2 right there. But yeah, so everything looks good right here, so we can now submit this. And so we just click again on our button right there. We can submit it. If you edited anything within that file, that would change right there. But now it's submitted, and now we just have to wait for it to finish. All right, so now the geometry optimization completed. And so this time we can see that the computation actually didn't take as long as the first one. And that has to do with the fact that the first time around, right, it went through all the painful steps of getting all the geometry optimized. And so when we went to a more sophisticated basis set, right, the TPSSH is a little bit more sophisticated than the B3lib. It didn't have to necessarily do as much computational work. And so that's always a good approach, is to kind of work your way up, especially if you're working with really sophisticated molecules. Now that geometry optimization is done, the thing that we really want to do in this case, right, is going to be doing a frequency calculation. So if we click on View Job right here, right, we can see that everything worked, and we can get all of the data that we want out of this. And if we see right here, right, it only took 3 steps this time around to compute the geometry. But what we can do is use this new geometry right here, click all the way through, click OK. So what we're going to want to do is do the vibrational frequency calculation. So now we go here, go down, vibrational frequency calculation corrected. We click on this, Everything else here should be able to stay the same, right? The TPSSH, the def2 TZVP. The thing that we really want to change right here is going to be the advanced. So right now, as you can see, there's a new option available. It says type of frequency calculation. So there's two options. One is analytical, one is numerical. Now, the analytical is faster, but you can only use it with specific functionals, right? The numerical can be used with all of them, but it just takes a bit more time. And it's just simply the math behind how it approaches calculation of the vibrations. You don't really get much of a difference in terms of the actual values that you get out. But what I'm going to do now is just simply show you as an example. If we do run the analytical, that this computation is actually going to fail. So if we click on it and it runs, right, it's going to go right here, right? So we can see right here that the computation failed. And so now that the computation failed, right, what we can do is a good thing to do if a computation fails is to look at the output file. So there's three options right here, right? So one is view job, one is to view raw output, and then one is to restart the job. The best thing to do always is just simply to look at the raw output. So if we click on that, what we can do is we can actually look at the output file that gets generated and has all these different pieces of information in here. Now, here under warning, and the part that actually tells us, right, that the calculation didn't succeed, it tells us, right, analytical Hessians are not yet implemented for meta GGA functionals, which is what TPSSH is, and to use the numerical frequency calculation, right, which we have right there. So what we can do now is if we just simply go here to view job, we can click on that. We can, go through till we set up our calculation. And so now we have all of this. And so let me just change this name real quick, right? So Vib numerical. So we go under advanced, and so now we change this to numerical now, and we run this. And so now we can see that this computation actually succeeded successfully. So what we can do is we can click on the magnifying glass, right? We can see our computation right here. Now, one important thing to always do when a frequency calculation completes is actually making sure that the geometry that we had optimized is actually a geometry that's in the ground state, right? And when I'm talking about something that's in the ground state, I'm talking about all the vibrational frequencies are positive. Negative vibrational frequencies indicate that you're in a transition state, right? Where that frequency is actually, the movement from one ground state to another one. And so to look at that, we just simply go here to raw output, and we get, the full output file. So if you ever wanted to, right, for fun, you could always look through all of this. But what we're really just looking for is just simply the vibration. So if we type in VIB, it shows here all the vibrational frequencies. And so we can see here, right, 0 all the way up to 20. And so none of them are negative, right? So that tells us that we're in a ground state, so we're good. There's nothing else that we have to do in this case. And so what we can do now is, right, we can scroll down, and we'll get now here to vibrational modes. And so this right here shows all of the vibrational modes. It shows the frequencies, right, in wave numbers, right, CM-1. It also shows us the intensities right here. Now, the interesting things that you can do is you can look at the different vibrations. So if we're looking here at 1788, and we click on this one right here to view it, it shows us, where all the different atoms are going to be moving to in that vibration, right? So you can see how all that's going. A much better and easier way to visualize it is actually if we click on this animate button right here, right? This film strip, right? It shows us, what's actually happening. So we can see that, the one that we're looking at here is actually, the CO stretch, right? At 1788 wave numbers. And so that's, going pretty strong there. Now, one thing to note is that, these calculations, they're not, going to correlate directly one-to-one to experimental data, right? You always have to add in some type of scaling factor. So if we're looking at it right here, we can add that directly right here, right? So we have a scale factor of 1.0 is what it's put in, for now. But if we go to a database or if we find papers, right? So the database that I had listed was the one from NIST that has a variety of different functional combinations with different basis sets. If we find the combination for the one that we have, right, we can plug that number in. So we're using TPSSH and def2 TZVP. So if we go here and scroll over, we can see that, the scaling factor should be 0.964. So if we go back to our job, we type that in here, 0.964, and now we can simply apply that by clicking on this, rescale frequencies button. What it does here, right, is it rescales all these frequencies using that scaling factor. So we have the original value in parentheses, and then we have the new rescaled values right here in these values right here. So if we wanted to, what we can do is we can also plot this IR spectrum. So if we click on IR spectrum right here, the magnifying glass, that'll plot it out right here. So this is what the spectrum kind of looks like. There's a few different features that you can change, right? You can change the line widths. So if something has very broad lines, you can change that. If something has really thin lines, right, you can change that as well. The things that you can do up here is you can just simply save this image if you wanted to, and you could use that. Or a much better thing to do is actually export the data. And so if you export the data, what it does is it downloads all these files, or sorry, all these values as a .jdx file. And so that .jdx file, right, you can load that into Excel, and then you can plot it directly. So if you have the experimental data and you have this computed data, right, you can overlap the two of them within Excel, right, and you can make a nice plot there showing how closely your computed, spectrum actually matches what the experimental spectrum is in these instances. So right here, as I said, right, you can change out, the peak width. Right now it's set to 40. You can make it really narrow, right? If we set it to 10 and we looked at the spectrum, right, now we have really, really sharp peaks. And that's something that you're typically going to see, in an ATR or even, in a KBR pellet IR. But if you have something like a liquid, right, you'll probably have something that's broader. So we can broaden this out. And let's just say, we're broadening it out to 80. Right, and so now these look a lot broader, and so they kind of match then probably something that's more of a liquid value. And so, you can play around with the Gaussian width a little bit there, so that way, you can see what matches more closely with what my experimental data is, depending on, the type of IR that I had collected. And then everything else right here is still the same. So the big thing you really want to get out of it, right, is going to be the spectrum, and then being able to use the animations and identifying these things right here to identify, the main peaks that you're really looking at. And so in this case right here, right, the thing that we're really focused on was the carbonyl, right? And so we know that the carbonyl stretch corrected as it comes in at 1723.8 wave numbers.